have two talks to this afternoon. The first one is Fosco Loregian, which is starting now, and after Giuseppe Rosolini. So I'm starting with Fosco Loregian from Tallinn University of Technology. We talk about Coens of higher arity. So if to Fosco
Yes,
can
I'm
take the
ready.
power and
I've got the
the
power.
screen.
Okay, so yeah, first I would like to join you in thanking everyone, besides the speakers, of course, also the organizers and everyone who attended. Yeah, I have to say it's a pleasure to see ItaCa from both sides. I've been an organizer with you guys, and now I'm a speaker. I'm having fun on both sides. So, okay, the let's begin with the ritual plan of the talk. First thing I have to say is this is a report on a paper that recently appeared on Archive with the same title. And as you can see, it is a joint work with another person, Theo de Oliveira Santos, who is a very smart student from Sao Carlos in Brazil. Um, you can get in touch with him. He's very passionate about category theory and wanting to learn. The other thing I have to mention is that this paper, this preprint, came out actually from the idea for writing. It came out from a previous ItaCa issue because Alessio in this summer gave a talk about how to extend the notion of the natural transformation, and that talk was very pleasant, very full of good insights and ideas. And I feel this endeavor, a stream of ideas I was into for different reasons wouldn't have come to reality without Alessio's insight and without the talk and without all the discussion that followed. Uh, Even I also have to mention that I will use Alessio's framework, but in a slightly tweaked meaning with some modifications here and there. But I will try to be precise about the modifications that I will employ. This talk, this material is quite heavy on the combinatorics because there are indices, bedices, P's and Q's everywhere. But I will do my best to keep it readable and easy to understand. There will be a part where I will discuss where this is going and why on earth we wanted to study this stuff, and you will see at the end. Anyway, so let's begin with the real talk. Okay, the most pleasant way in which I think this talk could begin is by saying that at the beginning of 20th century, a modest employee at Bern Patent's office had quite an interesting idea. Maybe that's one of the reasons, maybe the most important reason why we remember him. This idea is that many computations in tensor analysis in differential geometry can be simplified if we suppress all the summation symbols, because we can implicitly agree that the summation symbol is there whenever we pair a covariant and a contravariant index in a tensor. So very scary expressions like these, if I remember well, this is the Ricci curvature of a Riemannian metric, can become quite more compact, especially if you have to carry them on for pages and pages of computation. In category theory, this operation of summing over repeated indices can be thought as corresponding to the operation that takes a coend of a functor. Coends, as you at this point know very well, can be considered for functors that have this particular arity, where they depend covariantly on a variable and contravariantly on the other. Why? Because this operation is akin to taking the coproduct of all the images of TCC, where C is a single object of the domain of T, And then you mod out this sum by a certain equivalence relation. And well, the analogy with matrices is very easy to motivate, because there you can build a bicategory where the arrows are called profunctors, and in some sense they behave like matrices, and the composition of these gadgets behave like matrix composition. And of course, the summing operation is replaced by a coend, and the fact that you multiply matrix entries over the same entry B, over the same element B, is paralleled by integrating over B. Okay, so the question I had in the back of my head for quite some time is, what about tensors of higher arity, where, for example, the dependence of T is contravariant on some components and covariant on other components, but the number of the contravariant components and that of covariant components do not match. And if any, is this theory well behaved? If such a theory exists, is it well behaved as the one that can fill an entire book? Well, literally. Can we find applications? Can we find these unbalanced tensors, these higher arity ends and coends in nature, in mathematical practice, or elsewhere? And the answer is yes. You can write down a theory, and Alessio's insights were fundamental in this direction, because he provided the naturality condition for which we want to search universal objects. And what about the behavior of these things? Well, somehow some aspects of the resulting theory are not exactly satisfactory, but essentially because it's been quite difficult to find strong examples. There are some. I will not concentrate on those, but there are some, mostly because they take quite a lot of space. And well, is the resulting theory useful? This depends on your definition of useful. At least I can say that this theory can capture some interesting and even some new phenomena. The main motivation will be, for me, will be clear at the end of the talk. So let's postpone that for the moment. For the moment, same. I can say that one interesting fact is that there was this result, very well known since, I don't know, more than 40 years, that the set of denatural transformations between two functors having arity CO times C can actually be expressed as an end. The same, of course, is true if F and G depend only on one component, C covariantly or contravariantly, depends. For F and G of mixed arity, of arity CO times C, the trick is to compute the end of this functor where you have taken components, you have switched the A and B component on F, and you have kept them in the same order in G. Essentially, you compute the equalizer that defines this thing, and what you get is exactly the set of denatural transformations. Well, in the framework that Theo and I wrote down, this is a very elementary example of a 2-2 end, because you will see the definition exactly matches. And you can do the same when F and G have, let's say, type P and PQ. I will employ this notation for meaning that F is a functor from C to the P opposite times C to the Q. Okay, so first we need the notion of a generalized notion of denaturality, and that's where Alessio's work comes in. I have to say at the outset, this notion is, Alessio's notion is too general for the purpose that I had in mind, Theo and I had in mind, essentially because Alessio takes into consideration the case where a transformation, understood as a family of maps, generically taken, can be natural or dinatural or whatever at a single component, and unnatural, not even natural, not even the natural, in the other components. So this is slightly too general for our purposes, but even more importantly, Alessio takes care of denaturality for between functors that have different arity, different types. F goes from CPQ to D, and G goes from CRS to D. This is also too general for our purpose, mostly because we want to consider wedges and co-wedges where either F or G is constant. So either PQ or RS disappear in this framework. So a small point on notation, I will always consider a category like reordering all this, a product category, reordering all the contravariant, all the COP terms, and also the C terms on one side and on the other side, respectively. And I will call, as I already said, a functor that goes from CPQ to D of type PQ, mostly to be faster in telling you the story. Okay, so another point on notation, as you can see, things become quite hairy when you have to take care of different number of variables on the left and on the right, on the contravariant and covariant side. We have to take into account tuples. So tuples like this split into a prime component and a second component, well, where the A prime has length Q and the other has length P. I will mostly comply to the convention that contravariant components are superscripts and covariant are subscripts. And yeah, whenever, unfortunately, in Beamer, this notation is not exactly readable, but this is a boldface A. Whenever you see a bold, so a slightly fatter letter, that means that I have repeated A, the same symbol, the appropriate number of times. And if I don't do this, the notation explodes, literally explodes. Okay, so first, the main definition, finally. If I have two functors, F and G of types PQ and QP, note that the types are inverted for F and G, then PQ to QP, the natural transformation, is a collection of maps. And note again that F is P times contravariant and Q times covariant, and G the other way around. So this family of arrows defined for every object A in C must render the following diagram commutative. As you can see, this is just the denaturality hexagon. I have just replaced enough time the morphism F from A to B in the appropriate contravariant component of F, and then covariant Q times, and then Q times in the contravariant components of G, and respectively in the P covariant components of G. So see, you can see that the arity is switched for a reason that will also appear probably not evident, but motivated later. Okay, so the idea is just you want to connect the action that F has covariantly and contravariantly with the action that G has covariantly and contravariantly. An example is easily written because, for example, if P and Q are 2 and 1 respectively, then you have to find a denatural transformation. A 2-1 denatural transformation is a collection of maps defined for every A, such that this diagram commutes, where you see F takes 2 times the morphism F in the contravariant component, etc., etc. Quite easy. Okay, first question, what's with this PQ to QP? Alessio defines a more general notion of denaturality, which could be dubbed PQ to RS, because P is different from R and Q is different from S. We could have stuck to that notion, or we could have defined PQ to PQ denaturality. In the first case, considering constant functors either in the domain or the codomain, not much would have changed. So we stuck to the simpler nomenclature and the simpler terminology. In the second case, some theorems would have been quite tricky to state because the straight-to-book example above is very more difficult to state if you state the definition without switching the arity, the contravariant part, and with the covariant part of F and G. Okay, so our notion, as you can see, sits in the middle. And as I already said, when defining wedges and co-wedges, where F or G are constant, nothing changes much. The definition of wedge and co-wedge is absolutely not surprising because you essentially assume that either the domain or the codomain is constant. And so a PQ wedge for a functor of type PQ is just a family of maps where the domain is constant that makes this square commutative for every morphism F from A to B. And dually, a PQ co-wedge is the exact dual thing. So a family of maps towards to a common codomain, making a certain square commutative. For the moment, everything is very classical, and we are just reproducing the classical theory. So you see, the key step was exactly finding what the correct notion of the neutrality was, and also, of course, the wedge and co-wedge condition. Okay, so again, no surprise in the definition of end and coend, because there is a category of wedges and a category of co-wedges for a fixed D, a fixed diagram D of type PQ. And if the terminal object in the category of wedges exists, then that's the PQ end. And if the initial object in the category of PQ co-wedges exists, then that's called the PQ coend. The next few slides will be a very, I don't want to say boring, but there are a lot of sanity checks to perform here. For example, what we defined is a functor just because it's defined via a universal property. So you get functors from the category of diagrams of type PQ to the codomain that send a diagram to its end or coend, PQ end or coend. There is an interesting connection, in my opinion, between wedges as defined here, PQ wedges and co-wedges, and classical wedges and co-wedges. And the bridge connecting these two notions is just an iterated version of the diagonal functor. Essentially, what is the theorem? You have this functor delta PQ, which is defined as this iterated product of the good old diagonal functor or the opposite thereof. And there is an equivalence between this functor that, of course, is defined sending, This is defined sending a diagram in its category of wedges with a fixed tip or domain or codomain for wedges or co-wedges. And you can pre-compose with the PQ diagonal functor. And what you get is a diagram of type 1-1. Well, for that, you can consider the old category of wedges and co-wedges. And this gives you, if you compute these categories, these functors are isomorphic. And this means essentially that you can characterize the PQ end of a diagram as a classical end of the same diagram pre-composed with the PQ diagonal functor. Okay, and of course, dually, something similar holds for co-wedges and PQ coends. Okay, so yeah, this is essentially what I said, but with a slide. So maybe let's say again that there is this canonical isomorphism between the PQ end, as I defined it above, and the classical end, the 1-1 end of D pre-composed with the diagonal. Okay. Again, there is a limit formula for computing these things because the wedge property can be stated in terms of being the equalizer of a certain diagram, and dually the Coend property is stated in terms of being a co-equalizer. And the maps, again, are induced by the action of the diagram you want the end or the coend of on arrows, on morphisms. You just have to keep track, to take care of the iterated number of the iterated action of the on morphisms. Okay. Slightly more conceptually, one can say that ends and coends are limits and co-limits by proving that there is this fibration along which I can pre-compose a diagram. So, for example, I can compute the end of D as the limit of D pre-composed with the projection from a certain category, which is called the twisted arrow category. And this for the classical side. There is an analog for this construction in the PQ world, where you can define the PQ twisted arrow category and pre-composing with the projection from this twisted arrow category gives you the end as a limit and the coend as a co-limit. Again, no surprise. Since ends and coends are defined via limit operation and co-limit operations, you can show that the Ohm functor commutes with ends and coends, respectively, in the covariant component and in the contravariant component. And again, you can prove this has been quite hairy to assess, the Fubini theorem, that essentially says that I can integrate on some variables and then on some other variables, mostly because indices come in the way, and it's not really easy to understand. It wasn't really easy to understand what we wanted to prove, but in the end we did it. So if you take a diagram that has domain of this form, a to the pq times b to the rs to d, then you can equally compute the p plus r, comma, q plus s and over the pair ab, or you can iterate first the integral over b and then over a, or you can do the other way around, first over a and then over b. And same for coends. So the proof is conceptual, because in the end we found a conceptual argument. We found a way to copy the classical argument that essentially says all these procedures are universal, are canonical, are functorial, and I can characterize ending as ending a diagram as a right adjoint functor. So I can compose right adjoints in this way, in this other way, or I can take the composite right adjoint, and that's going to be, that must be isomorphic as a result. Okay, so what's not true, which was the original statement for the Fubini rule for higher arity ends, is that I can reduce the arity by saying that a PQ end can be computed as the end of a P minus 1, Q minus 1 end, and then iterating again, this would result in just a iterated application of classical ends. Mostly because the integrating over the pair AB in the product AB, this should be a B, is not the same as integrating over all the variables taken as a single one. Okay, so examples. Now you might expect examples. I have to postpone them at least, mostly because they take a lot of space. It's not that there are no examples. On the contrary, they are quite a lot, but developing all the nomenclature would take quite some time. So again, you can, in the paper, there is a whole section dedicated to examples, and maybe we can discuss them later. Instead, I would like to concentrate on some counterexamples, not examples, or at least some cases where this construction turns out to be trivial. For example, one could say, let's consider the category of modules over a ring, and let's consider the 0-2 end or the 0-2 coend of the functor that sends a module over on its iterated tensor product. Well, it turns out that this construction is trivial. If I take the end or the coend of this guy, then I must obtain the 0 module. This hides a quite general fact that if C is a shifted category, then all diagonal functors must be final. And so because of the property that I described above, there is no difference between doing an Eiger arity end or coend and taking just the classical end or coend of the same diagram, because the precomposition acts without changing the result. So another example that turns out to be semi-trivial is considering a bisimplicial set and then trying to compute. This is, you can look at this as the non-additive, the non-abelian analog in some sense of the previous construction in a very probably a stretched sense. But it turns out that if I consider the 2-0 coend of a bisimplicial set, what I get is an object that has a certain compact universal property. It's just a set of connected components of the diagonal of X. And the end dually is not exactly interesting because I just get X of 0, 0 by a quite easy computation by checking the universal property. More importantly, there is a PQ analog of the theorem I stated at the beginning, straight to book theorem, where we can not only characterize the d-natural transformations between f and g of type 1,1 as a 2-2 end, but the d-naturals of type between functors of type PQ as a PQ end. But the proof is exactly the same, just instead of 2-2, you take P and Q. Okay, instead, now I want to concentrate on another interesting definition that Theo and I found, which is, we decided to call it the Kuzarigama construction. Okay, I've already gave a talk on this topic and I tried to explain what is a Kuzarigama. I can say, I could try again, but instead I would like to show you a video. A Kuzarigama is a Japanese weapon that was used by ninjas, and that's the usage. You whirl a very heavy weight over your head and you try to catch the katana of the opponent while disarming him and killing him, like with a sickle, with a chop of your sickle. So why the name of this gadget? Well, you will see in a second. First, I would like to give you some motivation for this construction. This construction essentially works as a way to swap the type of a functor. But most importantly, so you take a diagram of type PQ, and the Kuzarigama eats this diagram and spits out a diagram of type QP. Most importantly, though, this construction is interesting because it builds an equivalence between the natural transformations of type PQ, between functors of type PQ, and natural transformations between F and the Kuzarigama of G, or natural transformation between the co-Kuzarigama of F and G. So in particular, this construction says, this equivalence says that these two constructions are adjoint functors. This is the Kuzarigama and this is the co-Kuzarigama for obvious reasons. The most important property of this construction, besides the adjointness property, is that they provide a very explicit way to build the universal fibration that I mentioned before. Because if I consider the functor of type PQ to the category of sets, which is constant at 1, then I can consider its co-Kuzarigama, and the result is a category, is a diagram which encodes the universal vibration that I mentioned above. This makes it possible to express the P, Q end and co-end as limits over a construction that is itself defined via a PQ end or a PQ coend, because explicit constructions for these guys can be given with the following super long integral. The Kuzarigama, let's concentrate on the second row for a second. The Kuzarigama of a functor applied to x and y, there are tuples of objects, is obtained as the QP end of this very long chain of iterated products of own functors, where the superscript here is the integration variable, and instead here A is a subscript, a covariant variable. These are the variables on which the functor, the Kuzarigama depends. And then I take the internal ohm or the power construction that I have in my sufficiently complete or co-complete category with G saturated on all the diagonalized, completely symmetrized. So you see, somehow this is the motivation behind the name. We have a sickle, we have a chain of ohm functors, and then in the end we have weighting with the diagram I want to compute the Kuzarigama of. So I hope this is enough as a motivation for the nomenclature. Okay, next step. I don't know how much time do I have because I can see the clock from the full screen.
Yes, Fosco, you have about less than 10 minutes.
Okay, I need very little. I planned, if I was short on time, I planned to avoid these two slides, where essentially I'm saying that this construction can be performed if I know the 1-1 Kuzarigama. I can take a suitable CAN extension and I can build the PQ Kuzarigama, and dually for the co-Kuzarigama. So this is quite technical and not particularly insightful, so I was ready to skip it and just mention it like this. Instead, I would like to show you how to define the PQ twisted arrow category of C. Okay, you take the PQ Kuzarigama of 1, where 1 picks out the terminal object of set, and then you take the comma category, the comma construction of this cospan. What you get is a category that has a vibration over CPQ. And this guy, twisted PQC, is exactly the category you need for recovering the limit, co-limit description of ends and coends in this higher arity work. Explicitly, this has a very concrete description when C at least has finite products and co-products, because this amounts exactly to a category of matrices of maps. Objects are morphisms between a p-fold coproduct to a q-fold product, and morphisms are factorizations of the codomain G through the domain in the form of maps from B1 to B1 prime, etc., and maps from A1 prime to A1, etc., that I can consider the p-fold coproduct of or the q-fold product of. Okay, quite a tongue twister. Now, let me spend 3 minutes on additional motivations and future plans, because in these future plans, there is most of my original motivation for entering this project. I met Theo on Matterflow after he asked a question, which was on the lines of, we all know and love limits, we all know and love weighted limits, and we all know and love ends and coends. What about weighted ends and coends? They should stand in the same relation as weighted colimits stand to colimits. Is it possible to define them? And my answer was yes. And in fact, you can, of course, you can try to scribble down a conjecture for what your definition is. It turns out that there are quite some examples of this construction. And it turns out that there is a very tight link between the theory, if any, of weighted end and the theory of Eiger arity ends. Because as in the same way, a weighted limit can be expressed as an end between the diagram and the weight, a weighted end is an Eiger arity end between the diagram, T, and the weight, W. Probably this D should be a T or vice versa, but you get the idea. And yeah, not only this, but one can define a whole new world of categorical concepts when weighing stuff, because you can weigh Can extensions, and what do you get? No one knows. You can weigh natural transformations, you can weigh monads, you can weigh adjunctions, you can weigh whatever. The other motivation is related, but I don't know, at this point, I don't know up to which point. Essentially, a very notorious negative property of the natural transformations is that they do not compose. They can't be composed in general. Alessio also gave a very clever way of recognizing when you can compose two dinaturals, but in general they don't. Point is that in this framework, in this picture, you probably can weigh the object of natural transformations between two functors enough in such a way that you shouldn't care about this obstruction for denaturals to compose. Because instead of composing a denatural between F and G and one between G and H into a denatural between F and H, what I can do in general maybe is falling into the set of weighted denatural transformations between this should be a denat, sorry. And also the others, I'm sorry. I can fall in the set of denaturals that are weighted by a certain weight that is obtained by ohming between them the ohm functors. And given that I did this once, I can iterate this, and I can do it 3 times, 4 times, n times. So probably a possible solution to the fact that denaturals do not compose could be moving to a setting where I don't have natural transformations, denatural transformations, and that's it. I have an entire hierarchy of higher and higher diagonality or denaturality, where in some sense the denaturality at level n, namely weighted by the ohm functor, the n-fold ohm functor, and denaturality at level m, in the same meaning, their composition, whatever it is, it falls into denaturality weighted by the n plus n-fold composition of the ohm functor. Again, this is very conjectural and probably very sketchy, but I wanted to give you an account of things we were discussing, I don't know, 2 weeks ago. And yeah, okay, so this is the very end of the talk, because this is really something we are in the process of thinking. So if you have questions, if you have suggestions, if I'm saying something blatantly false, please tell me, tell us. I welcome any comment. So that's the end of my talk.
So I'd like to thank Fosco for his talk, and I'm asking if there are questions or comments. Please just unmute your mic and speak.
If I may, I have a couple of questions. Well, to be precise, 3, but the first one is not a true question.
Okay.
First of all, just to see if I understood correctly, is the usual formulation of the ohm tensor adjunction a kind of 2-1 to 1-2 denatural transformation? Since I have 3 variables.
They must be the same variable. And in general, a 2-variable adjunction is stated in terms of it's stated more generally. But I think, I don't know. As you can imagine, computations are quite elusive in this setting. So even an easy conjecture can take some space to be written. But I think, no, yeah, I mean, you can feel my pain, because writing the paper was quite a mess. I'm not exactly a Bourbakist mathematician, so being precise and not losing an index is very difficult for me. But I don't know. Maybe, yes.
Okay, so maybe the other two questions will be easier, because you can simply say to me, okay, leave the room, please.
No, that's for Giuseppe. Not for the speaker.
Yes.
So anyway, the two main examples I have in mind in my small universe of end and coends are the Tanaka-Klein reconstruction, which can be realized as a coend, and the Takeuchi cross product, which is actually a combination of an end and a coend. So concerning the Tanaka part, do you think that this PQ arity can give a more general Tanaka reconstruction with some potential application I cannot see presently?
I don't know, essentially because I can't see in what way. My understanding as the coend guy, my understanding of Tanaka duality is you take a monoidal category with duals and some bells and whistles, and then you take the end of x times x dual.
Yeah.
And this is an interesting object because it's an algebra, bi-algebra, etc., etc. What would you like to do in taking into account P and Q more generally? You want to take P fold, a tensor product of P times the dual and Q times the object, and see what happens?
Much more naively, I was hoping to get rid of the dual, convert the contravariant part into a covariant part, and have a kind of Tanaka that is holding for categories.
Somehow, without Tanaka, this is exactly what I showed here. But this turns out to be zero. Not only the end, but also the coend, for a very stupid reason. You see, the fact that the domain category is shifted makes much more trivial the resulting theory. So, but this is exactly what you asked, and the answer is you get the zero module.
What a pity. Okay.
That's life.
Makes sense.
What about the other question?
The one about the Takeuchi product is
okay.
The Takeuchi product is a kind. First, I take a coend that gives me a tensor product. Then I take an end, which gives me the invariance with respect to a couple of actions. And this, in some categories, works almost as a tensor product in a monoidal category, but the problem is that it is not associative. I suspect that associativity is in some sense related to the fact that you can switch ends and coends, or have bigger ends and big coends that allows you to define, don't remember if it is called a semi-monoidal category or an almost monoidal category.
If it's not associative, it's called skew monoidal.
Skew monoidal. Oh, thank you very much. Yeah.
Okay, there is a very well-developed theory of which limits commute with which colimits. Not exactly very well developed, but at least we have main examples and quite pervasive examples. For ends and coends being commutative one over the other, I haven't done a real computation here, but I think it's much more restrictive. So because it's a condition on the domain of the functor, you take the end and the coend over. On the codomain, for sure, because the usual filtered versus finite limit commute with colimit philosophy works in the category of sets, and elsewhere it's pretty hairy to recover. Point is, I have no idea, because the condition on the gut feeling is that the condition that an end commutes with a coend is quite restrictive. So you might end with very trivial examples.
Okay, thanks.
But again, I'm not an expert. I'm just shooting in the dark.
So thank you, Paolo. And are there any other question?
I wanted to ask a question. Fosco, the way you raise the complexity of the of your factors, meaning that so you have something of kind PQ, and then you move it to something which is SZ using this operator that you invented. Reminded me of differential forms where you have this derivation process. You take the external derivative, which is given precisely by a sum, a very special kind of sum, and a very special kind of sum, and then which takes into account partial derivatives, and then you put some well, I mean, the theory of external differentials.
Yeah, the RAM differential. Yeah.
Yeah, and I wanted to know whether there is if you thought about this in this perspective, and if this makes some sense in your language.
Okay, I have absolutely no idea. Because mostly because I don't really see the connection that you speak of. I mean, I have the definition in front of my eyes, and I have the external derivative definition in the back of my head. They kind of communicate because yeah, both are some kind of generalized sums, but that's pretty much it. If you see something deeper, tell me. I have no idea. But it's funny because quite at the same time I started thinking about this, I was wondering as a parallel project, what if I take a category that is as, I don't know, a monoidal product and coproducts, and the monoidal product is co-continuous. So I have enough structure to define an endofunctor of this monoidal category, which is a derivation. So it's preserves coproducts and it's Leibniz. What's the deal here? What am I getting? And for a few days, I was wondering if there is a connection between these two questions, because they really came into my mind at the very same moment. Not because of a mathematical reason, but now that you put the derivation stuff on the table, maybe that's a sign of destiny.
So I think that our time is running over. So we can postpone if there are other questions after the second talk. And meanwhile, I'd like to thank Fosco again for his very, very interesting talk. And